Chapter 8 is about second order circuits. So 7 was first order circuits, meaning we had one charge storage element. We had either an inductor or capacitor in our circuit. With a second order circuit, you're going to have an inductor and a capacitor in the same exact circuit. And so we end up with a second order differential equation. The first section is 8.2, and it's finding the initial and final values. So in Chapter 7, we had to just find these here, right? And that was all we needed. But now in Chapter 8, since it's a second order differential equation, we're going to need, and I don't even know if that's on the screen, but we're going to need more initial values. So really the only way to do this is through an example. So I've drawn a circuit here that we're going to take a look at. Switch closes at time t equals 0. We have a capacitor and an inductor in this circuit. So let's look at the moment right before time 0. So at t equals 0 minus. And I think I'm going to go ahead and draw that in a different color just to try to keep it easier to see here. So let me write that again. So right before time 0, that's what 0 minus means. So right before time 0, this switch is open. We have a DC circuit, and our inductor will look like a short, and our capacitor will look like an open. So let's draw that circuit. Switch is open, and my capacitor will look like an open. It's like an open in DC. That's from Chapter 6. My inductor will look like a short, and then I have my source. So my inductor was there. Current I is still located there. This is my 10 ohms. We did not draw the switch because it's open. And we're looking for V across here. Okay, so this is pretty simple right here, right? We have these resistors in series, so my current is V over R. Oh, that's not a 20, that's a 12. 20, 12, a little bit different. 12 over 2 plus 10, or 1 amp. And my voltage, now I have my current. I'm looking for the voltage here. That is the voltage across here. That's the same thing. So I'm looking for the voltage across the 2 ohms. I could do voltage division, but I don't need to. I already have the current. V equals IR equals 1 times 2, or 2 volts. There's my first two initial conditions. This is my V of 0 and my I of 0. Go ahead and put those in a box, because we will need those later. Okay, now let's look at just after the switch opens. So I'm going to draw a circuit for t equals 0 plus. And what do I know about this, just the moment after, after the switch closes? So this is the time just after the switch closes. Well, I know voltage across the capacitor cannot change abruptly. So I know that V of 0 minus is equal to V of 0 plus, or we just call it V of 0, and it's 2 volts. And likewise, my current cannot change abruptly through my inductor. So I know I have 1 amp there. So let's look at the circuit again here, after that switch closes. So switch closes, it just closed, so we are not in steady state yet. I have to draw my capacitor and my inductor. So this switch has closed. What does that mean for this 10 ohm resistor? Think about it. So the switch is closed, this is connected to this, that 10 ohm resistor's crap, right? It's like it's not even there. I don't need to worry about it. It's shorted out. Does not exist. 12 volts. So this I and this V are known because of this right here. All right, so what else can I find now? I could find the voltage across my inductor. So if I draw let's draw a VL across the inductor, and it's gotten really messy here, so I'm going to move this current over here just to get it out of my way here. So I can use KVL, and I get minus V minus VL plus 12 equals 0, or VL equals 12 minus V. Well, I know V, right? This initial condition we found is 2. So VL is 10. And I know that the current through an inductor, let me write it a different way real quick. I know from chapter 6 that L di dt equals the voltage across an inductor. So now I can plug in what I need here to get my di dt. So my di dt is VL over L, or 10 over 0.4. di dt is, what do I have? It's 25, and it's amps per second. So there's one of my initial conditions that I was looking for. I still need one more, right? I still need my, which one have we not found? My V. No, yes, my dV dt, this one right here. Well, I also know this. I know that C dV dt is equal to the current through a capacitor, or di dt equals, I keep losing my spot here, IC over C. But I don't know my current through my capacitor, right? I know this current, but when I get here, this current splits. Some of it goes that way, some of it goes that way. So I don't know that current. So that's not going to work. But we could look at doing a KCL there. I know this current because I know V. This current is what I'm looking for, and I know this current. So I can write that let's see, IC is leaving, let's call this IC, call this IR. So I have IR leaving, IC, and I entering. So I have IC equals IR minus I. IR is going to be this voltage V, which is this, 2 over 2 ohms, minus my I, initial I through here is 1, or 0. I got IC equals 0. Plug that in up here, and I'm going to get di dt equals 0, and that's amps per second. So there's my fourth initial condition. So you have to remember when you're doing these to use this equation and to use this equation, and remember to do KVL and KCL to find the initials. Now the finals are pretty easy. That's what we did before in chapter 7. I don't know that this is going to fit on here, but if I look at my original circuit here, and my final value is going to look like this circuit, except where this is an open and this is a short, right? Because if it's been that way a long time, then my capacitor looks like an open, my inductor looks like a short. So that resistor doesn't exist. I'm not going to bother drawing it. I have a short, and I have 12 volts. So this is my I of infinity. This is the circuit for t equal infinity. This is my V of infinity. This is 2. So what's your V infinity? That's pretty easy, right? This is just in parallel with the source. So V infinity is 12 volts, and I infinity is going to just be 12 over 2, or 6 amps.